Tonight, we're embarking on a journey to understand one of the deepest mysteries in all of nature: gravity. This is the force you experience in every moment of your existence. It holds your feet against the ground beneath you. It wraps the protective atmosphere around our planet. It guides Earth in its endless dance around the sun. And it shapes the motion of entire galaxies, stretching across billions of light years of space. But here's something that might change the way you see everything around you. Gravity isn't really a force at all. It's something far more elegant, far more strange than we were ever taught to imagine. The truth about gravity touches everything from the rhythm of your heartbeat to the fate of the entire cosmos. It connects the simple act of dropping a cup to the spiraling dance of black holes in the depths of space. Before we begin, if you're finding this exploration meaningful, a simple like or subscribe helps this channel continue. It seems small, but it truly makes a difference. Now, let's step into this journey together and discover what gravity actually is. Let's peel back the layers of what we thought we knew and glimpse the deeper reality underneath. Think about what you believe you understand about gravity. When you release an object from your hand, it falls toward the ground. Simple enough, isn't it? Since childhood, you've been taught that Earth's gravity pulls objects downward. That gravity is some invisible force tugging you toward the center of the planet. That the sun's gravitational pull keeps Earth locked in its orbit. Most people accept this explanation without question. Schools present it as settled fact. And while this picture isn't entirely wrong, it's far from complete. It's a bit like saying Earth is flat because the ground appears flat when you're standing on its surface. The idea works well enough for everyday life, but it conceals a much deeper reality. Our intuitive understanding of gravity works perfectly fine for throwing a ball, building a bridge, or launching a satellite. But when we look more carefully, when we probe the extremes of strong gravity or high speeds, that simple picture begins to crack. The cracks reveal something far more beautiful and profound lurking underneath. Consider this for a moment. You're sitting or standing right now, feeling the solid ground beneath you. You feel your weight pressing down. This sensation feels so natural, so obvious, that questioning it seems absurd. Yet by the end of this journey, you'll understand that what you're actually feeling isn't what you think it is. The ground isn't holding you up against gravity's pull. Something much stranger is happening. Isaac Newton solved the mathematics of gravity back in 1687. That was when he published his monumental work, Mathematical Principles of Natural Philosophy. Most people simply call it the Principia. This book stands as one of the most significant scientific achievements in human history. It's difficult to overstate just how revolutionary this work was. Before Newton arrived on the scene, explanations for why objects fell or why planets moved were mostly philosophical speculation. Ancient Greek philosophers believed that objects fell because they were seeking their natural place in the cosmos. Heavy things belonged on Earth, so they naturally moved downward toward it. Fire and air rose because they belonged in the heavens above. It was a poetic idea, but it didn't really explain anything. It just labeled the phenomenon without providing any predictive power. You couldn't use it to calculate where a cannonball would land or when an eclipse would occur. Newton transformed everything. He demonstrated that the same force causing an apple to drop from a tree branch also governs the moon's orbit around Earth and Earth's journey around the sun. This insight was revolutionary. People had assumed the heavens operated under completely different laws than earthly phenomena. The celestial realm was considered perfect and eternal, while the Earth was imperfect and changing. Newton unified them all under one elegant set of mathematical principles. Imagine what this meant for the human understanding of the cosmos. Suddenly, the moon wasn't some mysterious celestial object following inscrutable divine laws. It was falling toward Earth, just like that apple. Except it was also moving sideways, fast enough that it kept missing Earth as it fell. The moon is perpetually falling around our planet. Every planet is perpetually falling around the sun. This was a profound conceptual leap. The story of Newton and the apple has become legendary, though whether it actually happened remains debated. What we know is that Newton spent years developing his ideas about gravity. He worked on the problem intermittently, combining mathematics with physical insight. The mathematics required to describe planetary orbits precisely didn't yet exist, so Newton essentially had to invent it. This led to his development of calculus, independently discovered around the same time by German mathematician Gottfried Leibniz. Newton's work was incredibly comprehensive. The Principia doesn't just describe gravity, it lays out fundamental laws of motion that still bear his name today. The first law states that objects in motion stay in motion unless acted upon by a force. The second law relates force, mass, and acceleration. The third law proclaims that every action has an equal and opposite reaction. These laws, combined with the universal law of gravitation, could explain virtually every observed motion in the heavens and on Earth. The impact was revolutionary. For the first time, human beings had a mathematical framework that could predict the future positions of planets with remarkable accuracy. Astronomers could calculate exactly when eclipses would occur, years or even centuries in advance. Navigators could use these predictions for more accurate timekeeping, essential for determining longitude at sea. The practical applications were immense. Newton's law of universal gravitation tells us that every single object in the universe attracts every other object. Not just planets and stars, but everything. Every atom, every speck of dust, every grain of sand. The strength of this attraction depends on two things. First, it's proportional to the product of their masses. Second, it decreases with the square of the distance between them. Let me make this clearer. Earth and your body pull on each other with considerable strength because Earth possesses enormous mass. You and a pencil sitting across the room also exert a gravitational pull on each other, but the force is so incredibly weak that you'd never detect it. In fact, the gravitational attraction between ordinary objects in everyday life is so small that it's essentially impossible to measure without extraordinary equipment. Just how weak are we actually talking about? Imagine trying to build a detector sensitive enough to register one person walking past your laboratory. The measurement arms would need to stretch roughly the distance from our Sun to Saturn. That's approximately 10 billion kilometers, or about 6 billion miles. Anything shorter than that, and the tiny signal would be completely overwhelmed by quantum fluctuations and thermal vibrations. The random jittering of atoms from heat, the quantum uncertainty inherent in measuring any position, these effects swamp the gravitational signal between human-scale objects. This is why you can easily feel the tug of even the smallest magnet or the shock of static electricity from a doorknob. Yet two people standing just 1 meter apart attract each other gravitationally with a force less than the weight of a single bacterium. Think about that. The electromagnetic force is so much stronger than gravity that a refrigerator magnet can easily overcome the gravitational pull of the entire Earth when it holds up a piece of paper. That paper contains countless trillions of atoms all being pulled downward by our entire planet, yet a tiny magnet defeats all of that pull without effort. Gravity is 39 orders of magnitude weaker than the electromagnetic force on everyday scales. 39 orders of magnitude means a number with 39 zeros after it. It's almost incomprehensible how much weaker gravity is. This represents one of the deepest unsolved puzzles in all of physics. Why is gravity so extraordinarily weak compared to the other fundamental forces? We don't have a satisfying answer yet. It's one of the great mysteries still waiting to be solved. And we haven't even discussed the inverse square law yet. This is a beautiful mathematical pattern that appears throughout nature. When you double the distance between two objects, the gravitational pull doesn't simply drop by half. It falls to 1/4 of its original strength. Triple the distance, and the force drops to 1/9. Quadruple the distance, and it drops to 1/16. The force decreases as the square of the distance increases. This mathematical relationship has profound consequences. It explains why gravity only dominates when masses become truly enormous. Near Earth's surface, gravity feels strong because we're so close to all that mass, but travel just a few thousand kilometers up and gravity's pull weakens noticeably. The International Space Station orbits only about 400 kilometers above Earth's surface, yet astronauts there experience about 90% of Earth's surface gravity. They float not because gravity has vanished, but because they're in continuous free fall, a concept we'll explore more deeply later. Newton's equations worked with stunning precision. They could predict planetary motion with remarkable accuracy. They explained the ocean tides, the rhythmic rise and fall of water caused by the moon's gravity pulling on Earth's oceans. The moon pulls more strongly on the side of Earth facing it, and less strongly on the far side. This creates a bulge of water on both sides of our planet. As Earth rotates beneath these bulges, coastal regions experience high and low tides. The sun contributes too, creating especially high spring tides when sun and moon align, and lower neap tides when they're at right angles. Newton's laws revealed why planets farther from the sun move more slowly in their orbits. Mercury whips around the sun in just 88 Earth days. Venus takes 225 days. Earth takes 365.25 days, which is why we have leap years. Mars requires 687 days. The pattern continues outward. Neptune, the most distant planet, takes over 164 Earth years to complete a single orbit. This happens because gravity weakens with distance according to that inverse square law. More distant planets feel weaker pull from the sun, so they move more slowly in their longer orbital paths. Newton's equations even allowed scientists to discover new planets by observing tiny irregularities in the paths of known worlds. That's exactly how Neptune was found. In 1846, astronomers noticed something puzzling. Uranus wasn't moving precisely as Newton's equations predicted it should. Uranus was discovered in 1781 by William Herschel, the first planet found with a telescope rather than visible to the naked eye. For decades, astronomers carefully tracked its motion across the sky, but Uranus kept wandering slightly off its predicted path. The deviations were small but unmistakable. Something was tugging on Uranus, pulling it slightly away from where it should be. Scientists had two options. Either Newton's laws were wrong, which seemed unlikely given their success elsewhere, or there was another planet out there, yet undiscovered, whose gravity was affecting Uranus. They performed careful calculations to determine where an unknown planet would need to exist to produce those deviations. The mathematics was challenging. They had to work backward from the observed effects to infer the location and mass of the unseen cause. Independent calculations by both John Couch Adams in England and Urbain Le Verrier in France arrived at similar predictions. Then they aimed their telescopes at that exact spot in the sky, and there it was, Neptune, sitting right where the mathematics had predicted This discovery was a triumph of theoretical astronomy. A planet had been found not by accident or systematic searching, but by using mathematical equations to predict where it must be. It demonstrated the incredible power of Newton's theory. The equations didn't just describe what we could see, they predicted things we hadn't seen yet. This is the hallmark of a truly powerful scientific theory. For more than 200 years, Newton's laws stood as the final authority on gravity. Scientists considered the problem essentially solved. Gravity was a force. It followed an inverse square law, and Newton's equations could calculate everything you needed to know. Universities taught Newtonian mechanics as established truth. Engineers used it to design bridges and buildings. Astronomers used it to predict eclipses and planetary positions with extraordinary precision. But there were small cracks in the foundation, tiny anomalies that didn't quite fit. Most scientists assumed these were measurement errors or unknown sources of interference that would eventually be explained within Newton's framework. The most famous of these anomalies involved Mercury's orbit. Mercury travels around the Sun in an ellipse, and this ellipse slowly rotates over time. We call this precession. Picture Mercury's elliptical orbit as if it were drawn on a piece of paper. Over time, that ellipse itself rotates, so the point where Mercury comes closest to the Sun, called the perihelion, slowly shifts position. Newton's equations predicted how much Mercury should precess based on the gravitational influence of the other planets. Each planet tugs on Mercury slightly, causing this gradual rotation of the orbit, but the actual observations didn't quite match. Mercury was precessing about 43 arcseconds more per century than the calculations predicted. To put that in perspective, 1 arcsecond is 1/3600th of a degree. An arcsecond is so small that it's about the angle subtended by a dime viewed from 2 miles away. 43 arcseconds per century is roughly 1/18th of a degree per century. Incredibly tiny, but undeniably real and measurable. Astronomers of the late 1800s and early 1900s measured positions in the sky with exquisite precision. They used long baseline instruments and careful techniques to eliminate errors. The discrepancy in Mercury's precession was far larger than their measurement uncertainties. It was a real effect demanding explanation. Scientists searched desperately for explanations. Perhaps an undiscovered planet called Vulcan was tugging on Mercury from somewhere between it and the Sun. This seemed plausible given Neptune's successful discovery through similar reasoning. Telescopes searched, but Vulcan didn't exist. No planet was there. Some astronomers thought they glimpsed something during solar eclipses, but these sightings were never confirmed. Vulcan was a phantom. Maybe Newton's laws needed some small adjustment for objects moving in strong gravitational fields. Perhaps the inverse square law wasn't quite exact. Maybe gravity decreased as distance to the power of 2.00001 instead of exactly 2. Physicists tried various modifications, but nothing worked satisfactorily. Any change that fixed Mercury's orbit would break something else that Newton's original equations got right. The mystery persisted unsolved until 1915, when Albert Einstein published his general theory of relativity. Einstein had been working on gravity for nearly a decade by that point. He knew Newton's theory, while extraordinarily successful, had conceptual problems. For one thing, Newton's gravity acted instantaneously across any distance. If the Sun suddenly vanished, Earth would immediately fly off into space, even though the Sun is 8 light minutes away. This instantaneous action at a distance troubled Einstein because it conflicted with special relativity, which he had published 10 years earlier. special relativity said nothing could travel faster than light, including information about changes in gravitational fields. Einstein's insight cut to the very heart of reality. Gravity isn't a force pulling objects together. Instead, it's a curvature of space-time itself. Now, that probably sounds like abstract nonsense. Curvature of space-time. What could that possibly mean in concrete terms? Let me walk you through this step by step, building from ideas you already grasp intuitively. First, consider space and time as separate things, the way we normally experience them. Space is the three-dimensional arena where everything exists and moves. You can travel forward and backward, left and right, up and down. Those are your 3 dimensions of space. Any location in space can be specified by 3 numbers, 3 coordinates. In a city, you might use street address, cross street, and floor number. In open space, you might use latitude, longitude, and altitude. 3 numbers uniquely identify any position. Time seems fundamentally different. It flows steadily in one direction, from past toward future. You experience events in sequence, one after another. You cannot move backward through time or leap arbitrarily forward. Time feels like a one-way river carrying you along. Space and time appear to be completely separate categories. Space is where events occur. Time is when they occur. They seem to have nothing to do with each other beyond both being needed to specify when and where something happens. But Einstein showed us that space and time are not actually separate entities. They're woven together into a single 4-dimensional fabric that we call space-time. This isn't merely some mathematical convenience or clever trick. It's a description of physical reality itself. You cannot have space without time, or time without space. They're different aspects of the same underlying structure. This unification came from Einstein's earlier work on special relativity in 1905. He realized that the speed of light is the same for all observers, regardless of their motion. This simple but profound insight led to remarkable consequences. If light speed is constant, then measurements of space and time must adjust to compensate. Moving observers experience time passing more slowly and distances appearing contracted. But this raised a puzzle. Special relativity worked beautifully for objects moving at constant velocity in the absence of gravity. But what about acceleration? What about gravity, which everyone experiences constantly? Einstein pondered this for nearly a decade, searching for a way to incorporate gravity into the relativistic framework. The breakthrough came from what Einstein later called his happiest thought. He imagined a person falling freely from a roof. That person would feel weightless during the fall, just as if they were floating in space far from any gravitational field. This suggested something profound. Free fall is the natural state. Gravity isn't a force acting on falling objects. Gravity is the curvature of space-time, and free-falling objects are simply following natural paths through that curved geometry. When you move through space, you're simultaneously moving through time. When time passes, you're also traveling through space-time. Even when you're sitting perfectly still in space, you're still moving through space-time. You're moving through the time dimension at 1 second per second. Every event that happens anywhere in the universe occurs at a specific location in space-time. Not just a position in space and a moment in time separately, but a unified 4-dimensional coordinate in space-time itself. Think about planning to meet a friend. You need to specify 4 pieces of information. Where in space you'll meet, which requires 3 coordinates, like an address, and when in time you'll meet, which requires 1 coordinate, like 4 o'clock on Tuesday. Those four numbers together specify an event in space-time. The meeting exists as a single point in this four-dimensional structure. You and your friend each travel through space-time along different paths called world lines that intersect at the meeting event. This might seem like mere semantics, just a fancy way of describing what we already knew. But treating space and time as unified leads to profound consequences. Special relativity, Einstein's earlier theory, showed that different observers moving relative to each other will disagree about measurements of space and time. What one person measures as a purely spatial separation might appear to another as part space and part time. The split between space and time depends on your motion. This only makes sense if space and time are aspects of a unified space-time. Now here's where things become fascinating. Space-time is not rigid and unchanging. It's flexible. It can bend and curve and stretch. And what causes space-time to curve? Mass and energy. Any object possessing mass or energy curves the space-time surrounding it. The more massive an object is, the more dramatically it curves space-time. Earth curves the space-time around it into a gentle depression. Our Sun curves space-time far more severely because it contains so much more mass. Even your own body curves space-time by a tiny, immeasurable amount. Everything possessing mass or energy curves space-time to some degree. This is Einstein's central revelation. Matter tells space-time how to curve, and curved space-time tells matter how to move. It's a beautiful reciprocal relationship. Gravity isn't a force at all. It's geometry. When you see an object falling, you're not watching a force pull it downward. You're watching it follow the natural curves and contours of space-time itself. Imagine space-time as a stretched rubber sheet pulled tight across a frame. If you place a heavy bowling ball on this sheet, it creates a dip, a depression in the surface. The heavier the ball, the deeper the dip it creates. Now, if you roll a marble near this bowling ball, the marble won't travel in a straight line. It curves toward the bowling ball, following the slope of the depression. From the marble's perspective, it's simply following the straightest path available across the surface. But because the sheet itself is curved, that straightest path ends up curving toward the bowling ball. Earth works in a similar way. It curves the space-time around it. When you drop a ball, that ball isn't being pulled downward by some invisible force. Instead, it's following the straightest possible path through curved space-time. That path just happens to curve toward Earth's center. The ball is simply doing what objects naturally do in curved space-time. It's following a geodesic, the curved space equivalent of a straight line. Now, this analogy has important limitations. The rubber sheet is a two-dimensional surface being bent into a third dimension. But space-time is four-dimensional, and it's not bending into some higher dimension that we can point to. It's what we call intrinsically curved. The curvature is a property of space-time itself, not a bending into something external. Also, in the rubber sheet analogy, we're actually using gravity itself to make the ball sink into the sheet. That's circular reasoning when we're trying to explain gravity in the first place. So while the analogy helps with visualization, don't take it too literally. The mathematics of general relativity describes curvature precisely without needing to invoke any external space or any force to create the curvature. Mass and energy simply curve space-time around them. That's just what they do. What does it actually mean for space-time to be curved? In flat space-time, the kind you'd have with no mass or energy present, the rules of geometry work exactly as you learned in school. Parallel lines never meet. The angles of a triangle always add up to 180 degrees. The circumference of a circle is always 2 times pi times the radius. These are the rules of Euclidean geometry, named after the ancient Greek mathematician Euclid. But in curved space-time, these familiar rules break down. Parallel lines can converge or diverge. Triangle angles might add up to more or less than 180 degrees. A circle's circumference might not equal 2 pi times its radius. The geometry itself changes. This is real, measurable curvature that affects how objects move and how light travels. Consider the surface of Earth as a simple example of curved geometry. On a flat map, if you draw a triangle and measure the angles, they add up to 180 degrees, just as Euclidean geometry predicts. But draw a large triangle on Earth's curved surface. Start at the North Pole, go down to the equator, travel 1/4 of the way round the equator, then return to the North Pole. You've drawn a triangle with 3 90-degree angles. 3 angles of 90 degrees add up to 270 degrees, not 180. The surface of Earth is curved, and this curvature changes the rules of geometry. Space-time curvature around massive objects works similarly. The geometry changes in ways that affect how objects move through space and time. Here's the key insight that makes general relativity so beautiful. Objects moving through curved space-time follow what we call geodesics. A geodesic is the straightest possible path through curved space. In flat space, geodesics are simply straight lines. But in curved space, geodesics themselves curve. When you're in free fall, experiencing what feels like weightlessness, you're actually following a geodesic through curved space-time. You're not accelerating at all from your own perspective. You're traveling the straightest path available. The astronauts aboard the International Space Station are in constant free fall, following a geodesic that curves around Earth. They feel weightless because they're following a natural path through curved space-time with no forces acting on them. The station is falling toward Earth just like any dropped object would. But it's also moving sideways fast enough that as it falls, Earth's surface curves away beneath it at the same rate. The station keeps missing Earth as it falls. It follows a geodesic that forms a closed loop around our planet. The astronauts inside are also following geodesics through space-time. From their perspective, they're not experiencing any forces. They feel weightless because they're in natural free fall. Here's something that might surprise you. Right now, as you sit or stand on Earth's surface, you are accelerating. You're not following a geodesic. The ground beneath you is pushing upward, constantly accelerating you away from the geodesic you would naturally follow. That's why you feel weight. You feel the force of the ground pushing up against you, preventing you from following your natural path through curved space-time. If the ground suddenly vanished, you'd begin falling. But from the perspective of general relativity, falling is the natural state. It's standing still that requires force. This completely inverts our intuitive understanding. We think of gravity as a force pulling us down. We think of the ground as passively supporting us, holding us up against that downward pull. But Einstein revealed the truth is exactly opposite. There is no downward pull. There's only curved space-time defining natural paths through it. The ground is actively pushing you, accelerating you away from your natural geodesic. That push, that acceleration away from freefall, is what you experience as your weight. Gravity isn't pulling you downward. Instead, Earth's mass curves space-time, and that curvature defines the geodesics. The electromagnetic forces in the ground, the repulsion between atoms that keeps solid objects from passing through each other, push you away from your geodesic. That push is what you perceive as weight. This has profound implications for how we understand acceleration. In Einstein's view, there's no difference between the force you feel standing on Earth and the force you'd feel in a rocket accelerating through empty space at 9.8 meters per second squared. Both prevent you from following a geodesic. Both feel identical from your perspective. This is called the equivalence principle, and it's foundational to general relativity. You cannot tell the difference between gravitational effects and acceleration effects through any local experiment. If you're inside a closed room with no windows, no amount of experiments performed inside that room can tell you whether you're sitting on Earth's surface or accelerating through space in a rocket at 1 Earth gravity. They're the same thing. A person in a closed box with no windows cannot determine whether they're standing on Earth's surface or in a rocket accelerating through empty space. This equivalence principle led Einstein to the full theory. If gravity and acceleration are equivalent, and if we know from special relativity that acceleration affects the flow of time, then gravity must also affect time. Time itself must flow at different rates in different gravitational fields. This sounds like science fiction, but it's measurably real. We'll explore this remarkable consequence in detail shortly. Now, what actually creates this curvature in space-time? Mass and energy. But the relationship is more subtle than you might expect. It's not just the amount of mass that matters. It's also how that mass is distributed, how it's moving, and even pressure within the material. All of these contribute to the curvature. Momentum contributes. Stress contributes. Even pressure contributes. Einstein's field equations, the mathematical heart of general relativity, describe precisely how mass, energy, momentum, and pressure tell space-time how to curve. And then, once space-time is curved, that curvature tells matter how to move. It's a beautiful, self-consistent relationship. Matter curves space-time. Curved space-time guides the motion of matter. Each influences the other in an intricate dance. The equations capture this interplay with remarkable elegance. Physicist John Wheeler summarized it beautifully when he said, "Space-time tells matter how to move. Matter tells space-time how to curve." The field equations are complex, involving mathematical objects called tensors and techniques from differential geometry. Solving them exactly for most situations remains extremely difficult, even with modern computers. But the basic principle is elegant. More mass and energy mean more curvature. Concentrate that mass into a smaller volume and the curvature becomes more extreme. This is why dense objects like neutron stars and black holes produce such extreme gravitational effects. They pack enormous mass into tiny volumes, creating steep curvatures in space-time. In weak gravitational fields, like here on Earth's surface, or throughout most of the solar system, Einstein's equations produce predictions nearly identical to Newton's laws. That's why Newton's laws worked so well for so long. They're an excellent approximation when gravity is relatively weak and objects move slowly compared to light speed. For launching satellites, building structures, even landing robots on Mars, Newton's equations work perfectly fine. The corrections from general relativity are too small to matter for practical purposes. But in strong gravitational fields, or when objects move at significant fractions of light speed, the predictions diverge. Only Einstein's equations give correct answers in these extreme conditions. Near black holes, around neutron stars, in the first moments after the Big Bang, or when detecting gravitational waves, general relativity is essential. Newton's laws simply break down under these conditions. One of the strangest predictions of general relativity involves time itself. Time doesn't flow at the same rate everywhere. In regions where space-time is more strongly curved, time passes more slowly. This isn't some optical illusion or measurement error. Time genuinely flows at different rates depending on the strength of the gravitational field. This effect is called gravitational time dilation. Near a massive object, where space-time curvature is steep, clocks tick more slowly compared to clocks farther away, where spacetime is less curved. The difference is real and measurable. This is not just that clocks run slow. Time itself passes more slowly. Every process, every physical phenomenon, runs slower deep in a gravity well. Chemical reactions proceed more slowly. Light oscillates at lower frequencies. Heartbeats pulse more slowly. Everything. Consider two identical clocks. Place one on the ground and one at the top of a mountain. The clock on the ground experiences slightly stronger gravity because it's closer to Earth's center. After enough time passes, the two clocks will show different times. The clock on the ground will have ticked fewer times than the clock on the mountain. Time literally passed more slowly for the ground clock. For everyday heights, the difference is minuscule. We're talking nanoseconds over a day for a mountain height difference. But it's real, and we can measure it with precise atomic clocks. Experiments have been performed where atomic clocks were placed at different altitudes, then brought together and compared. The predictions of general relativity were confirmed to extraordinary precision. The clock at lower altitude had ticked fewer times. Time had passed more slowly for it. This has practical consequences. The Global Positioning System, GPS, relies on a network of satellites orbiting Earth. Each satellite contains precise atomic clocks. These satellites orbit at about 20,000 kilometers altitude, where Earth's gravitational field is weaker than at the surface. Time runs faster for these satellites compared to clocks on Earth's surface. The difference is about 45 microseconds per day. That might not sound like much, but light travels about 30 centimeters, or roughly 1 foot, in 1 nanosecond. 45 microseconds corresponds to about 13 kilometers of position error per day. If GPS didn't account for gravitational time dilation, your navigation system would accumulate about 13 kilometers of error every day. Within minutes, the system would become useless for navigation. But there's another effect too. The satellites are also moving at about 4 kilometers per second relative to Earth's surface. Special relativity tells us that moving clocks run slow. This velocity time dilation causes the satellite clocks to run about 7 microseconds per day slower than ground clocks. Combining both effects, gravitational time dilation speeds the satellite clocks up by 45 microseconds per day, while velocity time dilation slows them down by 7 microseconds per day. The net effect is that satellite clocks gain about 38 microseconds per day compared to ground clocks. Engineers must program the satellite clocks to tick at a slightly different rate to compensate for both effects. The clocks are intentionally run slow before launch, so that once in orbit, experiencing both gravitational and velocity time dilation, they tick at exactly the right rate to stay synchronized with ground clocks. This is general relativity at work in everyday technology you probably use without thinking about it. Every time you use GPS to navigate, you're relying on corrections derived from Einstein's equations. The system wouldn't work without understanding how gravity curves space-time and affects the flow of time. Your smartphone contains technology that requires understanding general relativity. This theory isn't just abstract physics for astrophysicists studying distant stars. It's part of everyday life, invisibly but essentially. Time dilation becomes more extreme near more massive objects. Near a neutron star, time would pass noticeably slower than on Earth. If you spent a year on the surface of a neutron star and then returned to Earth, you'd find that significantly more time had passed on Earth. The exact difference depends on the neutron star's mass and size, but it could be days, weeks, or even months. This is real time travel into the future, allowed by the laws of physics. Visit a strong gravitational field, experience time flowing slowly, return home to find the future has arrived. Near a black hole, the effect becomes truly dramatic. Imagine you watch a friend falling toward a black hole while you remain at a safe distance. As your friend approaches the event horizon, the boundary beyond which nothing can escape, something strange happens from your perspective. Your friend appears to slow down. Their movements become sluggish. They get closer and closer to the event horizon, but never quite seem to reach it. They appear frozen, hovering just outside, with light from them becoming increasingly redshifted and dim. This isn't an optical trick or illusion. Time itself flows differently in the extreme curvature near the event horizon. From your distant perspective, an infinite amount of time would pass before your friend actually crossed the horizon. You would watch them approach asymptotically, getting ever closer but never quite arriving. The light from them would become more and more redshifted as time dilation increased, eventually shifting into infrared, then radio waves, then becoming undetectable. But from your friend's perspective, nothing unusual happens as they cross the event horizon. They fall through in a finite amount of their own time. They don't feel themselves slowing down or freezing. From their point of view, they cross the horizon smoothly, in perhaps a few seconds or minutes depending on the black hole's size. They don't notice anything special about the moment of crossing. The event horizon isn't a physical surface or barrier. It's just a mathematical boundary in space-time. The difference is entirely due to how time flows in different regions of curved space-time. Your friend's watch ticks normally from their perspective once per second, just as always. But each tick of their watch corresponds to a longer and longer interval of time from your distant perspective. As they approach the horizon, 1 second for them might correspond to a year for you, then a century, then millions of years. The time dilation approaches infinity right at the horizon. This is one of the most mind-bending aspects of general relativity. Different observers experience time differently depending on their location in a gravitational field and their relative motion. There's no single universal time that everyone agrees on. Time is relative, woven into the fabric of space-time itself, flowing at different rates in different places. Black holes represent the most extreme curvature of space-time possible. They form when massive stars exhaust their nuclear fuel and collapse under their own gravity. During most of a star's life, nuclear fusion in its core produces an outward pressure that balances gravity's inward pull. This balance can last billions of years, but eventually the fuel runs out. When fusion stops, there's nothing left to push outward against gravity. The core collapses catastrophically. For stars below a certain mass limit, the collapse is halted by quantum mechanical pressure between electrons, creating a white dwarf. For more massive stars, even this isn't enough. The collapse continues, forcing electrons to combine with protons and form neutrons, creating a neutron star. But if the star is massive enough, nothing can stop the collapse. The core compresses into an infinitely dense point called a singularity, surrounded by an event horizon. The event horizon is the point of no return. Once anything crosses it, not even light can escape. The curvature of space-time inside becomes so extreme that all paths lead inward toward the singularity. Even if you pointed a flashlight outward and turned it on, the light would curve back inward. Space-time itself is curved so severely that the very concept of outward ceases to exist inside the event horizon. The size of a black hole's event horizon depends on its mass. For a black hole with the mass of our Sun, the event horizon would have a radius of about 3 kilometers. For a black hole 10 times the Sun's mass, the radius would be about 30 kilometers. Supermassive black holes at galaxy centers, containing millions or billions of solar masses, have event horizons extending millions or billions of kilometers. Near the event horizon, tidal forces become enormous. These forces arise because gravity is stronger on the side of an object closer to the black hole than on the far side. This creates a stretching force. As you fell toward a black hole feet first, your feet would experience much stronger pull than your head. This difference would stretch you vertically while simultaneously compressing you horizontally. The technical term is spaghettification, and it's as unpleasant as it sounds. For stellar mass black holes, a few times the mass of our Sun, these tidal forces would tear you apart long before you reach the event horizon. You'd be stretched and compressed until molecular bonds broke, reducing you to a stream of atoms. But for supermassive black holes, millions or billions of times our Sun's mass, the event horizon is much farther from the center. The tidal forces at the horizon are surprisingly gentle. You could cross the event horizon of a supermassive black hole without immediately noticing anything wrong physically. You wouldn't be torn apart at the moment of crossing. Of course, once inside, you couldn't escape. All possible futures lead to the singularity. You'd have a short time remaining, perhaps hours or minutes depending on the black hole's size, before reaching the singularity and being crushed to infinite density. During that remaining time, you could look back out through the event horizon and see the universe outside time dilated. You might watch the entire future history of the universe unfold in those final moments. What happens at the singularity remains one of the deepest mysteries in physics. General relativity predicts infinite curvature and infinite density, but we know these predictions can't be literally true. At such extreme conditions, quantum effects become important, and we don't yet have a complete theory of quantum gravity to describe what actually happens. The singularity represents the point where general relativity breaks down, where our equations produce infinities and cease to give meaningful answers. Solving this mystery requires unifying general relativity with quantum mechanics, something physicists have been working on for decades without complete success. String theory is one approach. Loop quantum gravity is another. Both attempt to describe spacetime at the smallest scales where quantum effects cannot be ignored. But neither theory is complete or confirmed experimentally yet. The quantum nature of spacetime remains one of the greatest unsolved problems in theoretical physics. Black holes also demonstrate another remarkable feature of general relativity. They have no hair, as physicists say somewhat colourfully. This means a black hole is completely characterized by just three properties: mass, electric charge, and angular momentum or spin. Nothing else matters. It doesn't matter what fell into the black hole to create it, whether it was made from a collapsed star, or from compressed gas, or from anything else imaginable. The resulting black hole depends only on these three numbers. All other information about what went in is lost, seemingly erased from the universe. If you dropped a library full of books into a black hole, all that information would disappear. The black hole would increase in mass by the amount of mass in the books, but there would be no way to recover what was written in them. This leads to deep questions about information conservation in physics. Quantum mechanics says information cannot be destroyed, but black holes seem to destroy information. How do we reconcile this? Stephen Hawking spent much of his career grappling with this black hole information paradox. Despite being invisible themselves, black holes can be detected through their effects on surrounding matter. When gas falls toward a black hole, it forms an accretion disk. The gas spirals inward, orbiting faster and faster as it approaches. Friction between gas particles heats the disk to millions of degrees. At these temperatures, the disk emits intense X-rays before the gas crosses the event horizon and disappears. These bright X-ray sources often mark the locations of black holes. We can also detect black holes by watching how stars orbit around them. If a visible star orbits around an invisible companion, and we can calculate that companion's mass from the orbital motion, we can determine whether it's massive enough to be a black hole. If the companion mass exceeds about 3 times the Sun's mass and emits no light, it's almost certainly a black hole. There's nothing else that could be that massive, that compact, and that dark. In 2019, astronomers achieved something remarkable. They captured an actual image of a black hole's shadow. The Event Horizon Telescope, a global network of radio telescopes working together as a single Earth-sized telescope, imaged the supermassive black hole at the center of the galaxy, Messier 87. This galaxy lies about 55 million light-years away in the constellation Virgo. The black hole at its center contains about 6.5 billion times the mass of our Sun. The image showed a dark circular shadow surrounded by a bright ring of glowing gas. The shadow's size and shape matched predictions from general relativity precisely. The ring is the photon sphere, the region where light can orbit the black hole. The dark interior is the shadow cast by the event horizon. Behind the black hole, light from the accretion disk is bent around by space-time curvature, creating the bright ring we see. This was direct visual confirmation that black holes exist exactly as general relativity predicts, and that space-time curvature behaves as Einstein's equations describe. In 2022, they released an image of Sagittarius A star, the supermassive black hole at the center of our own Milky Way galaxy. This black hole contains about 4 million solar masses and lies about 27,000 light-years from Earth. Again, the image perfectly matched theoretical predictions. We're now routinely imaging black holes, turning these once theoretical objects into observable reality. General relativity makes another striking prediction. When massive objects accelerate, they create ripples in space-time itself. These ripples propagate outward at the speed of light, carrying energy away from the source. We call them gravitational waves. Imagine space-time as a fabric. When you shake a massive object back and forth, it sends ripples through the fabric, like waves spreading across a pond's surface when you splash your hand in the water. These gravitational waves alternately stretch and compress space as they pass. If a gravitational wave passes through you, traveling from left to right, you'd be very slightly stretched horizontally while being compressed vertically. Then the pattern would reverse, oscillating as the wave passes. The stretching and compression alternate perpendicular to the wave's direction of travel. Gravitational waves have a characteristic quadrupole pattern, stretching in one direction while compressing perpendicular to that. For typical sources, gravitational waves are extraordinarily weak. Even cataclysmic events, like colliding black holes, produce waves that stretch and compress space by less than 1 part in 10 to the power of 21 by the time they reach Earth. That means if you measured the distance from Earth to the Sun, approximately 150 million kilometers, a gravitational wave would change that distance by less than the width of an atom. To appreciate how small this is, consider that an atomic nucleus is about 10 to the power of negative 15 meters across. Gravitational waves change distances by amounts comparable to, or smaller than, this over distances of many kilometers. It's like measuring the distance to Alpha Centauri, over 4 light-years away, to the precision of a human hair's width. Detecting something so tiny seemed nearly impossible for decades, but scientists were determined. They built gravitational wave detectors called interferometers. These instruments use laser light to measure tiny changes in distance between mirrors separated by several kilometers. The basic idea is surprisingly simple, though the implementation is anything but. You split a laser beam in two, send each half down a long arm at right angles to each other, bounce them off mirrors at the ends, and recombine them when they return. If the arms have exactly the same length, the light waves arrive back in phase and interfere constructively. But if a gravitational wave passes through, it stretches one arm slightly while compressing the other. This changes the distances the light travels, causing the waves to arrive slightly out of phase. The interference pattern shifts in a characteristic way that reveals the gravitational wave passing through. The most famous detector is LIGO, the Laser Interferometer Gravitational Wave Observatory. LIGO has two facilities, one in Livingston, Louisiana, and one in Hanford, Washington State, separated by about 3,000 kilometers. Each facility has two arms, each 4 kilometers long, arranged in an L shape. Laser light travels down each arm, bounces off mirrors, and returns. The light from both arms recombines, and scientists look for interference patterns. Having two detectors separated by a continent helps confirm detections and determine the direction gravitational waves came from. The detectors had to be incredibly sensitive. They needed to detect distance changes smaller than 1,000th the width of a proton across 4 kilometers. To achieve this, engineers isolated the mirrors from every conceivable source of vibration. Earthquakes, even from the other side of the planet. Ocean waves on distant shores. Passing trucks on nearby highways. Wind. Thermal fluctuations from temperature changes. Seismic noise. Even quantum uncertainty in the laser light itself create noise that must be overcome. The mirrors hang from sophisticated suspension systems that filter out vibrations. The arms are in ultra-high vacuum to prevent air molecules from affecting the light. The laser is extremely stable. Noise cancellation systems continuously monitor and subtract known sources of interference. The technology pushed the boundaries of measurement precision to unprecedented levels. Building LIGO required decades of work and over $1 billion in funding. On September 14, 2015, after years of construction and calibration, LIGO detected its first gravitational wave signal. The signal came from two black holes, each about 30 times the Sun's mass, spiraling together and merging about 1.3 billion light-years away. The entire event lasted a fraction of a second. As the black holes orbited faster and faster, approaching the speed of light in their final moments, the signal frequency increased. This produced a characteristic chirp sound when converted to audio, rising in pitch before cutting off suddenly at the moment of merger. In that brief moment of merger, the collision released more energy in gravitational waves than all the stars in the observable universe combined emitted in light. Think about that. For that fraction of a second, those two merging black holes outshone every star in the cosmos, not in light, but in gravitational waves. 3 times the Sun's mass worth of energy radiated away as spacetime ripples in a fraction of a second. That's the mass equivalent energy of about 6 times 10 to the power of 47 joules, an almost incomprehensible amount of power. The detected signal matched the predictions from general relativity almost perfectly. The shape of the wave, its frequency evolution, the way it died away after the merger, the final ring down as the newly formed black hole settled into a stable configuration, everything aligned with computer simulations based on Einstein's equations. These simulations solve the field equations numerically for two black holes spiraling together. The match between prediction and observation was extraordinary. This was direct detection of gravitational waves, confirming another major prediction of general relativity a century after Einstein proposed the theory. Einstein himself doubted gravitational waves would ever be detected. He thought them too weak to ever measure. He would have been astonished by LIGO's success. Since that first detection, LIGO and other detectors have observed dozens of gravitational wave events. Most involve colliding black holes, but some involve neutron star collisions. Each detection provides a new way to study the universe. Gravitational wave astronomy is now a reality, opening a completely new window onto cosmic phenomena we could never see with light. Some black hole mergers occurred so far away or involved black holes surrounded by so little matter that they produced no light. Without gravitational waves, we'd never know these events happened. Gravitational wave astronomy lets us observe the universe in an entirely new way. One particularly exciting detection came on August 17, 2017. LIGO detected gravitational waves from two neutron stars spiraling together and merging. The signal lasted much longer than black hole mergers because neutron stars are less massive and orbit more slowly before colliding. About 2 seconds later, the Fermi Gamma Ray Space Telescope detected a gamma ray burst from the same location in the sky. This was thrilling. Then, over the following days and weeks, telescopes around the world observed light across the electromagnetic spectrum from the merger aftermath. Optical telescopes saw a bright glow that faded over days. X-ray and radio telescopes detected emission. Space-based infrared telescopes observed the cooling remnants. This was the first time a cosmic event was observed, both through gravitational waves and traditional light-based astronomy. We call it multi-messenger astronomy, using different types of signals to study the same event. The observations confirmed that neutron star mergers produce short-duration gamma-ray bursts and create heavy elements through rapid neutron capture, a process called the R process. When neutron stars collide, they eject clouds of neutron-rich material. Free neutrons are captured rapidly by atomic nuclei, building up heavy elements like gold, platinum, uranium, and thorium. The gold and platinum in Earth's crust, the gold in your jewelry, likely came from ancient neutron star collisions billions of years ago, before our solar system formed. Every heavy element in your body, heavier than iron, was created either in supernova explosions or neutron star mergers and scattered into space to eventually form new stars and planets. General relativity has been tested in many other ways beyond gravitational waves and black holes. One of the earliest tests involved light bending. Newton's theory actually predicted some light bending, treating light as if it were made of particles affected by gravity. But Einstein's theory predicted exactly twice as much bending as Newton's theory did. This was a clear, testable difference. Einstein's theory predicted that light passing near a massive object would follow a curved path through the curved spacetime. Light from a distant star passing close to the Sun should appear to shift position slightly when viewed from Earth. During a total solar eclipse in 1919, astronomer Arthur Eddington led expeditions to observe stars near the Sun's edge during totality. Normally, you can't see stars near the Sun because the sky is too bright. But during a total eclipse, when the Moon blocks the Sun's disk, stars become visible even close to the Sun's position. Eddington's team photographed the star field near the Sun during the eclipse, then compared these positions to photographs of the same star field taken months earlier when the Sun was in a different part of the sky. The stars appeared shifted from their normal positions by approximately 1.75 arcseconds, the amount Einstein predicted. Roughly twice what Newton would have predicted. This observation made Einstein internationally famous overnight. Newspapers around the world proclaimed that Newton had been overturned, that space was curved, that a new understanding of gravity had been achieved. Eddington's announcement came in November 1919, just after the end of World War I. Here was a German physicist's theory, confirmed by British astronomers, a symbol of international scientific cooperation after a devastating war. The public was fascinated. Einstein became a celebrity, the archetypal genius. It was dramatic confirmation that space-time really is curved. Today, we observe this light bending, called gravitational lensing, routinely. When light from a distant galaxy passes near a massive foreground galaxy or galaxy cluster, the light's path curves. This can produce multiple images of the background galaxy, distorting and magnifying it. Sometimes, the background galaxy appears stretched into long arcs. Sometimes it forms complete rings, called Einstein rings, if the alignment is perfect. These effects are exactly what general relativity predicts. Gravitational lensing is now used as a tool to study both the lensing objects and the distant galaxies behind them. It allows us to map the distribution of dark matter in galaxy clusters. Dark matter doesn't emit light, but it has mass, so it curves space-time and lenses background light. By observing how light bends around a cluster, we can determine where the mass is, including the dark matter. This is one of the key pieces of evidence for dark matter's existence. The way gravitational lensing reveals dark matter is elegant and undeniable. When we look at a galaxy cluster, we can count the visible stars and gas and estimate the total mass of normal matter. But when we observe how that cluster lenses background galaxies, the amount of lensing is far greater than the visible matter alone could produce. There must be additional unseen mass, roughly 5 times more than the visible matter. This invisible mass is dark matter. The distribution of dark matter can be mapped by carefully analyzing the lensing distortions. The results show that dark matter forms a halo around galaxy clusters, extending far beyond the visible galaxies. These dark matter halos likely pervade the universe, providing the gravitational scaffolding upon which visible structures form. We can even use gravitational lensing to magnify extremely distant galaxies, effectively using massive clusters as natural telescopes. Light from very distant, very faint galaxies is brightened and magnified when it passes through a massive cluster along our line of sight. This allows us to see galaxies we couldn't otherwise detect. Some of the most distant galaxies known, seen as they were less than 1 billion years after the Big Bang, were discovered this way. These distant galaxies appear as they were in the universe's youth, giving us glimpses of cosmic dawn, the era when the first stars and galaxies were forming. Another test involves the precession of Mercury's orbit that troubled astronomers in Newton's time. When Einstein applied his field equations to Mercury's motion, the equations predicted exactly the observed precession. 43 arc-seconds per century, matching observations perfectly without any need for arbitrary adjustments. No need to invoke a hidden planet Vulcan or modify Newton's laws. General relativity simply got it right naturally, as a direct consequence of how space-time curves around the Sun. This was one of the first major confirmations that Einstein's theory improved upon Newton's. Einstein himself later said that when he discovered general relativity correctly predicted Mercury's precession, he was so excited that his heart palpitated. He had spent years developing the theory, working through enormously complex mathematics. Seeing it successfully explain this long-standing anomaly was tremendously satisfying. Binary pulsar systems provide another remarkable test. Pulsars are rapidly spinning neutron stars that emit beams of radio waves from their magnetic poles. As they rotate, these beams sweep across space like lighthouse beacons. If one happens to point at Earth as it rotates, we detect regular pulses, often many times per second, with precision rivaling atomic clocks. Some pulsars pulse hundreds of times per second, spinning incredibly fast. Some pulsars are in binary systems, orbiting another star. As they orbit, gravitational waves carry energy away from the system according to general relativity. This causes the orbit to gradually shrink, making the orbital period decrease over time. The rate of orbital decay depends on the masses, separation, and orbital parameters in a way precisely predicted by Einstein's equations. In 1974, astronomers discovered PSRB 1913 plus 16, a system containing two neutron stars orbiting each other every 7.75 hours. This system turned out to be a perfect laboratory for testing general relativity. The orbital period decreases by about 76 millionths of a second per year. Over decades of observation, this matched the prediction from gravitational wave emission to better than 1 part in 1,000. The match is now even better. After 40 years of observations, the agreement between prediction and measurement is better than 1 part in 10,000. This was indirect evidence for gravitational waves existing and carrying energy away exactly as Einstein's theory predicted, decades before LIGO directly detected them. The discoverers, Russell Hulse and Joseph Taylor, won the Nobel Prize in 1993 for this work. General relativity also explains the universe at the largest scales. The theory predicts that space itself can expand or contract. This wasn't originally obvious. When Einstein first applied his equations to the entire universe, he found they predicted either expansion or contraction. A static universe seemed unstable. This troubled him because, at the time, in 1917, everyone assumed the universe was static and eternal. To force his equations to allow a static universe, Einstein added a term called the cosmological constant. This acted like a repulsive force on cosmic scales, balancing gravity's attractive pull. He later called this his greatest blunder when observations showed the universe actually is expanding. In the 1920s, astronomer Edwin Hubble made measurements showing that distant galaxies are moving away from us. Hubble used the new 100-inch Hooker telescope at Mount Wilson Observatory, then the largest telescope in the world. He observed galaxies and measured their distances using variable stars called Cepheids as standard candles. He also measured how fast they were moving away by observing the redshift of their light, the stretching of light wavelengths caused by the galaxy's recession. He found a relationship. The farther a galaxy is, the faster it recedes. Distance is proportional to recession velocity. This became known as Hubble's law. This wasn't because galaxies are flying through space away from some central point. Instead, space itself is expanding, carrying galaxies along with it. Imagine dots painted on the surface of a balloon. As you inflate the balloon, the dots move apart from each other, not because they're moving across the surface, but because the surface itself is stretching. Each dot sees every other dot moving away, with more distant dots receding faster. There's no center to the expansion on the surface. Every point is equivalent. Similarly, space expands uniformly everywhere. Galaxies aren't moving through space away from us. Space between galaxies is growing, carrying them apart. From any galaxy's perspective, it appears that all other galaxies are moving away, with distant ones receding faster. The expansion has no center in three-dimensional space. It's happening everywhere, simultaneously. The expansion of space has profound implications. If the universe is expanding now, it must have been denser in the past. Following this logic backward, we can imagine the universe in earlier and earlier times, becoming smaller, denser, and hotter. This leads to the conclusion that the universe began in an extremely hot, dense state about 13.8 billion years ago. We call this the Big Bang. The term Big Bang is somewhat misleading. It wasn't an explosion into space, but an expansion of space itself from an initially extremely small, dense state. In the earliest moments, the entire observable universe was smaller than an atom, unimaginably hot and dense. As space expanded, it cooled, much like gas cools when it expands. Particles formed when temperatures dropped enough. Then atoms formed. Eventually, under gravity's pull, matter clumped together to form the first stars and galaxies. The Big Bang theory, based on general relativity applied to the entire cosmos, explains the large-scale structure and evolution of the universe. Evidence for the Big Bang is overwhelming. First, we observe the expansion itself. Distant galaxies are receding, with velocity proportional to distance, exactly as an expanding universe predicts. The relationship is linear, just as general relativity predicts for a universe expanding uniformly. Second, we observe the cosmic microwave background radiation, often abbreviated CMB, the afterglow of the Big Bang. About 380,000 years after the Big Bang, the universe cooled enough for atoms to form. Before this recombination epoch, free electrons scattered light constantly, making the universe opaque like the interior of a cloud. Once atoms formed, electrons were bound in atoms and light could travel freely. That light has been traveling through space ever since. Because space has expanded during the light's journey, the light has been stretched from visible wavelengths to microwave wavelengths. We detect it coming from every direction uniformly, a nearly uniform glow with temperature of about 2.73 degrees above absolute zero. First detected accidentally in 1964 by Arno Penzias and Robert Wilson, the CMB is one of the strongest pieces of evidence for the Big Bang. Tiny fluctuations in this radiation, variations of about 1 part in 100,000, map the early density variations that eventually grew into galaxies and large-scale structure. Third, the abundance of light elements matches Big Bang predictions remarkably well. In the first few minutes after the Big Bang, when the universe was still incredibly hot and dense, nuclear fusion occurred throughout all of space. Protons and neutrons combined to form deuterium, helium, and traces of lithium in specific ratios determined by the temperature, density, and expansion rate of the early universe. Big Bang nucleosynthesis predicts about 75% hydrogen and 25% helium by mass, with trace amounts of other light elements. Observations of the oldest stars, formed from primordial gas before much stellar processing occurred, confirm these predictions. The agreement is excellent. This provides independent confirmation of the Big Bang model. These 3 pillars, expansion, cosmic microwave background, and light element abundances, establish the Big Bang theory as the best explanation we have for cosmic origins. General relativity predicted that space could expand before we'd even observed it. The equations contained this possibility naturally. Then, observations confirmed it. This shows the deep connection between the geometry of spacetime described by Einstein's equations and the large-scale behavior of our universe. The mathematics of curved spacetime, developed to explain gravity, ended up explaining the origin and evolution of everything. The expansion raises fascinating questions. What came before the Big Bang? That question might not even make sense. If time itself began at the Big Bang, asking what came before is like asking what's north of the North Pole. The question assumes time extends further back, but perhaps it doesn't. Time is part of space-time, and if space-time itself began at the Big Bang, then time began too. We don't know what, if anything, existed before or caused the Big Bang. Did something exist? Did time exist in some different form? Did other universes exist? These questions push beyond what current physics can address. Our understanding breaks down at the very earliest moments, the first tiny fraction of a second, when the universe was so hot and dense that quantum effects dominated space-time itself. Understanding those first instants requires a theory of quantum gravity that we don't yet have. Does the universe have an edge? not in any ordinary sense. If space is finite but unbounded, like the surface of a sphere, you could travel forever in one direction and eventually return to your starting point without ever encountering an edge or boundary. The sphere's surface is finite in area but has no edge. Similarly, three-dimensional space could be curved back on itself in a four-dimensional geometry, finite but unbounded. Or space might be infinite, extending forever in all directions. Current observations suggest the universe is very close to being spatially flat, geometrically speaking, which in most cosmological models would mean it's infinite. We measure the curvature by looking at the geometry of the cosmic microwave background. So far, we detect no curvature within measurement precision, but we can only observe a finite region, limited by the distance light has traveled since the Big Bang. This observable universe has a radius of about 46 billion light-years, accounting for expansion during the light's travel time. Beyond that, light hasn't had time to reach us yet. There might be infinitely more universe beyond what we can observe, but we have no way to know. The observable universe is all we can ever hope to study. The expansion has practical consequences for space travel and communication. As the universe expands, distant galaxies recede faster and faster. Eventually, sufficiently distant galaxies recede faster than light can travel through space toward us. This doesn't violate relativity because the galaxies aren't moving through space faster than light. Space itself is expanding, carrying them away. Light leaving a galaxy beyond a certain distance will never reach us, even though it travels toward us through space at light speed. The expansion of space carries the light away faster than it can approach us. This defines a cosmic event horizon, a distance beyond which we can never see or communicate with galaxies, no matter how long we wait. For galaxies beyond this horizon, we are causally disconnected. No information can pass between us, ever. Even more strange, because space itself is expanding, you could argue that distant galaxies are moving away from us faster than light, even though nothing can move through space faster than light. The resolution is that the speed limit applies to motion through space, not to the expansion of space itself. Space can expand at any rate, without violating relativity. Distant enough regions of space recede from us faster than light due to the accumulated expansion across vast distances. This means that some galaxies currently visible to us will eventually disappear from view as expansion carries them beyond the cosmic horizon. Over billions of years, more and more galaxies will fade and vanish, not because they're destroyed, but because the space between us expands too fast for light to ever traverse it. Information from those regions will be forever beyond our reach. The observable universe will actually shrink over cosmic time from our perspective. An astronaut traveling near light speed would experience time dilation from both special and general relativity effects. Special relativity tells us that moving clocks run slow relative to stationary observers. The faster you move through space, the slower your clock ticks from the perspective of someone at rest. This isn't an illusion. Time genuinely passes more slowly for the moving observer. If you travelled at 99% of light speed, time would pass about 7 times slower for you than for someone remaining on Earth. A journey that took 70 years from Earth's perspective would feel like only 10 years to you. At 99.9% of light speed, the time dilation factor increases dramatically to about 22. At 99.99%, it increases to 70. 70 years from Earth's perspective would be only 1 year for you. This has profound implications for interstellar travel. You could, in principle, travel to distant stars within a human lifetime from your perspective. But when you returned, if you returned, centuries or more would have passed on Earth. Everyone you knew would be long dead. Civilization would have changed unrecognizably. You'd arrive in a future era, unable to return to your own time. This is sometimes called the twin paradox, though it's not really a paradox. If one twin travels at high speed to a distant star and returns, that twin will have aged less than the sibling who remained on Earth. This isn't a paradox. It's a real, measurable consequence of how time flows differently for observers in relative motion. The travelling twin genuinely experiences less time passing. They don't just age less. Less time actually passed for them. For a trip to a star 100 light years away, travelling at 99.995% of light speed, the journey from Earth's perspective would take just over 100 years each way. But the traveller would experience only about 3 years passing in each direction. That's dramatic time dilation. The traveller could visit distant stars, but at the cost of becoming a time traveller into Earth's future. This isn't science fiction speculation. The mathematics is straightforward, confirmed every day in particle accelerators, where subatomic particles moving at near light speed live much longer than their stationary counterparts before decaying. Unstable particles called muons normally decay in about 2 microseconds when at rest. But cosmic ray muons, moving at 99.9% of light speed, reach Earth's surface from the upper atmosphere, surviving for what would normally be impossible given their short lifetime. Time dilation extends their life from their rest frame. The universe imposes a cruel trade-off. Travel fast enough and you can reach distant destinations within a human lifetime from your perspective. But everyone you knew on Earth will be long gone when you arrive, and possibly when you return if you do. You'd be travelling into Earth's future, emerging into a world centuries or millennia beyond your departure. There's no going back in time. You'd be a permanent, temporal exile. This is why, even with unlimited energy for propulsion, interstellar colonization faces profound challenges beyond just the energy requirements. Astronauts become temporal exiles, severed from their origin civilization, not just by distance, but by time itself. They'd arrive to find their home world transformed beyond recognition. Communication would be limited by light speed delays measured in years or decades each way. Any conversation would span generations. The expansion of the universe raises questions about its ultimate fate. Will it expand forever, or will it eventually stop and collapse back in on itself? The answer depends on the total density of matter and energy in the universe compared to a critical value. If the density is high enough, gravity will eventually halt the expansion and pull everything back together in what we call a big crunch, essentially a reverse of the Big Bang. The universe would collapse back to a singularity. If the density is too low, the universe will expand forever, becoming increasingly dilute and cold as time goes on. Stars will form and die, using up available gas. Eventually, star formation will cease. The universe will grow dark and cold. There's a critical density right between these extremes, where the universe is balanced, expanding forever, but at an ever-slowing rate, asymptotically approaching zero expansion. Measurements suggest the universe is remarkably close to this critical density. But there's an unexpected twist to the story, one of the most surprising discoveries in modern cosmology. The expansion isn't slowing down as you'd expect if gravity was the only factor. It's actually accelerating. The expansion rate is increasing over time. This discovery came in 1998 from studying distant supernovas. Type Ia supernovas are a specific type of stellar explosion that can be used as standard candles, objects with known intrinsic brightness. By comparing their apparent brightness to their known intrinsic brightness, we can calculate their distance. By measuring their redshift, we can determine how fast they're receding. 2 independent teams measured dozens of distant supernovas and found something shocking. The distant supernovas, seen as they were billions of years ago, were fainter than expected. This meant they were farther away than they should be if the universe had been expanding at a constant rate or slowing down. The only explanation was that the expansion has been speeding up. The discovery was so unexpected that it was initially met with considerable skepticism. Both teams checked and rechecked their data. Other groups performed independent measurements, but the result held. The universe's expansion is accelerating. Something is pushing space apart, counteracting gravity's pull. We call this mysterious component dark energy. We don't know what dark energy actually is. That's why it's called dark. It's one of the great mysteries of contemporary physics. It might be a property of empty space itself, a cosmological constant that Einstein once proposed for different reasons. Einstein added the cosmological constant to his equations to allow a static universe. He removed it when expansion was discovered, calling it his greatest blunder. But perhaps he was right after all, just for different reasons. Empty space might have an intrinsic energy density that doesn't dilute as space expands. Or dark energy might be a dynamic field filling all of space, something that varies over time and space. We call this quintessence. Either way, dark energy makes up approximately 68% of the total energy content of the universe based on current measurements. Dark matter contributes around 27%. Ordinary matter, everything we can see directly, all atoms, all normal matter, is only roughly 5% of the total. The universe is dominated by components we don't yet understand. This is simultaneously humbling and exciting. We've figured out so much, yet so much remains mysterious. The acceleration driven by dark energy has been going on for approximately the last 5 billion years. Before that time, the universe's expansion was actually decelerating due to gravity's pull. Matter density was high enough that gravity was winning, but as the universe expanded, matter became more dilute. Gravity's influence weakened because it depends on density. Dark energy's influence either remained constant or possibly even increased slightly depending on its exact nature. Eventually, about 5 billion years ago, dark energy took over. The expansion transitioned from decelerating to accelerating. Since then, the expansion rate has been increasing. In the far future, this acceleration will continue. Galaxies beyond our local gravitationally bound group will be pushed beyond our cosmic horizon by the relentless expansion. The observable universe will actually shrink over time from our perspective, even as space itself expands. Eventually, in trillions of years, the only galaxies visible will be those gravitationally bound to our local group, like Andromeda and the Magellanic Clouds. Everything else will have been carried away by the expansion of space, beyond our ability to ever observe. Future civilizations, if any exist, would see only their local group of galaxies in an otherwise empty, dark sky. They might never realize that billions of other galaxies existed beyond their horizon. The cosmic microwave background would redshift into undetectability. Future astronomers might have no evidence the Big Bang ever occurred. Even our local group of gravitationally bound galaxies won't last forever. In the far, far future, tens of trillions of years from now, stars will stop forming everywhere. All the available gas will have been used up or expelled from galaxies or locked up in remnant objects. Existing stars will gradually burn out. The longest-lived stars, small red dwarfs, might shine for tens of trillions of years, but eventually, even they'll exhaust their fuel. White dwarfs will cool into black dwarfs, dark cinders no longer emitting light, essentially frozen balls of carbon and oxygen. Neutron stars will remain, spinning slowly in the darkness, gradually radiating away their rotational energy. Black holes will persist, slowly accumulating any matter they encounter. The universe will become dark and cold, filled with scattered black holes, dead stellar remnants, and elementary particles spreading through ever-expanding space. Even black holes won't last eternally. They'll eventually evaporate completely through Hawking radiation, a quantum mechanical process where particle pairs form at the event horizon and one falls in while the other escapes, slowly reducing the black hole's mass. Larger black holes evaporate more slowly. A solar mass black hole would take about 10 to the power of 67 years to evaporate. Supermassive black holes take incomprehensibly longer, 10 to the power of 100 years or more. Hawking radiation represents one of the most profound discoveries at the intersection of quantum mechanics and general relativity. Stephen Hawking showed in 1974 that black holes aren't entirely black. They emit thermal radiation as if they have a temperature. This temperature is inversely proportional to the black hole's mass. Smaller black holes are hotter and evaporate faster. Larger black holes are colder and evaporate more slowly. For stellar mass and larger black holes, the temperature is incredibly tiny, far below the temperature of the cosmic microwave background. These black holes are actually gaining mass faster from absorbing background radiation than they lose through Hawking radiation. They're growing, not shrinking. But in the far future, after the universe has expanded and cooled far more, the cosmic microwave background will redshift to even lower temperatures. Eventually, it will become cooler than even supermassive black holes. At that point, all black holes will begin slowly evaporating. The evaporation process accelerates as the black hole shrinks. A black hole half the mass has twice the temperature and evaporates faster. As it loses mass, it gets hotter and radiates more intensely. In its final moments, a black hole would release a burst of radiation as it disappears entirely. But for supermassive black holes, this final burst wouldn't occur until unimaginably far in the future. Eventually, only a sea of photons and other particles will remain, spreading through ever-expanding space. The particles will become increasingly separated as space continues expanding. The universe will approach maximum entropy, a state of complete uniformity and equilibrium. This is called the heat death of the universe, the ultimate fate predicted by combining thermodynamics with general relativity. The universe reaches maximum entropy, uniform temperature approaching absolute zero, no remaining gradients to drive any process or allow any complexity. All the structure, all the beauty we see today will have dispersed into a cold, dark, nearly empty expanse. But that's trillions upon trillions of years in the future, timescales almost impossible to comprehend meaningfully. Numbers like 10 to the power of 100 years are so vast that they lose all intuitive meaning. To put it in perspective, the current age of the universe is less than 10 to the power of 10 years, only about 14 billion years. The far future timescales we're discussing are exponentially, incomprehensibly longer. For now, the universe remains vibrant and active and interesting. Stars are forming in stellar nurseries, great clouds of gas and dust where gravity pulls matter together. Galaxies are colliding and merging in spectacular cosmic dances. Black holes are growing as they consume surrounding matter. And we're here on this small planet trying to make sense of it all. We're witnessing the universe in its youth, cosmologically speaking. The era of stars and galaxies will last trillions of years, and we're experiencing it now. General relativity gives us the conceptual tools to understand gravity at every scale, from falling apples on Earth to the expansion of the entire universe. It's a remarkable intellectual achievement, connecting the smallest everyday phenomena to the grandest cosmic structures. One framework, one set of equations, explains everything from why you feel weight standing on Earth to why the universe began in a Big Bang and will eventually fade into darkness. Space exploration faces fundamental limitations imposed by physics itself. The vast distances and the absolute limit of light speed mean that interstellar travel presents enormous challenges. The nearest star system, Alpha Centauri, lies over 4.37 light-years away. Even if we could travel at 10% of light speed, far beyond anything our current technology can achieve, the journey would take over 43 years one way. At our current maximum speeds, achieved by the fastest spacecraft like Voyager, the journey would take tens of thousands of years. Accelerating a spacecraft to half light speed would require energy equivalent to all the electricity humanity generates in an entire year just for a probe with the mass of a single gram, roughly a paperclip. For a craft large enough to carry people with supplies, life support, and sufficient shielding from cosmic radiation, the energy requirements become truly astronomical. We'd need energy sources and propulsion systems orders of magnitude beyond anything we currently have. Various propulsion concepts have been proposed over the decades. Nuclear propulsion, using fission or fusion reactions, could potentially achieve a few percent of light speed. Antimatter engines, if we could somehow produce and store enough antimatter, might reach higher speeds. Light sails, pushed by powerful lasers, could accelerate slowly over long distances. Generation ships, where multiple generations live and die during the journey, could make very slow interstellar trips possible, in principle. All of these face enormous technical challenges. Perhaps interstellar travel with humans aboard simply isn't practical with any technology we can foresee. Maybe we're effectively confined to our solar system for the foreseeable future, for centuries or millennia at least. That's not necessarily a tragic limitation. The solar system itself is vast, with countless destinations to explore. Mars could potentially be terraformed over centuries or millennia, gradually transformed into a world with a thicker atmosphere and liquid water on its surface. It would require enormous effort, but it's theoretically possible using processes we understand. The moons of Jupiter and Saturn, particularly Europa, Enceladus, and Titan, harbour subsurface oceans beneath their icy shells. These are environments that might already contain life, evolved independently from Earth life. Exploring them could reveal the answer to one of humanity's deepest questions: are we alone? Asteroids could be mined for valuable resources, providing materials for construction in space without the expense of lifting them from Earth's gravity well. Water from asteroids could provide fuel through electrolysis. Metals could be refined and used for building. Large space habitats, positioned at stable Lagrange points, could house millions of people in comfortable, Earth-like conditions, with artificial gravity from rotation. The solar system could support a civilization far larger than Earth's current population, spreading across billions of kilometers while remaining connected by light-speed communications measured in hours, not years or decades, like interstellar communication would require. There's something profoundly sobering about the idea that every star might be forever beyond our physical reach. That we might be observationally and practically isolated, not because life doesn't exist elsewhere, but because the distances are simply too vast and the speed of light too absolute a limit. We can see countless stars, billions of galaxies. We can study them in detail, but we might never visit them. They might remain forever out of reach to travelers from Earth. General relativity tells us the universe operates on scales far beyond human intuition, placing fundamental constraints on what's possible. The speed of light is absolute. Time dilation is real. These aren't engineering challenges. They're fundamental properties of space-time itself. Yet there's also beauty in this recognition. It means that every moment we have is precious and unique. We're here, briefly, on cosmic timescales. But in that brief time, we can understand so much. We can measure the curvature of space-time itself using GPS satellites and atomic clocks. We can detect gravitational waves from black holes colliding billions of light years away, events lasting fractions of a second. We can image the shadows of supermassive black holes at galaxy centers. We can trace cosmic history back to the Big Bang's first moments, understanding how the universe evolved from a hot, dense state to the magnificent cosmos we see today. We're tiny creatures on a small planet, orbiting an ordinary star in a typical galaxy, who have somehow figured out the fundamental laws governing phenomena on cosmic scales. We've decoded the geometry of space-time itself. We understand how gravity works from the quantum scale to the cosmic scale. That's truly extraordinary when you step back and appreciate what we've accomplished. Think about where we started. Ancient humans looked up at the night sky and saw lights moving in mysterious patterns. They created myths and stories to explain what they saw. The gods were moving the stars and planets, they thought. The sun was carried across the sky in a chariot. The universe was small, centered on Earth, with the heavens just beyond reach above us. Over centuries and millennia, we slowly pieced together the truth. Earth isn't the center. It's a planet orbiting a star. That star is one of hundreds of billions in our galaxy. Our galaxy is one of hundreds of billions in the observable universe. We're incredibly small in the cosmic scheme, yet we've managed to understand the forces and principles governing scales from subatomic particles to the entire cosmos. We've learned that the universe is ancient beyond imagination, that it began in a hot, dense state and has been evolving for nearly 14 billion years. We've learned that the atoms in our bodies were forged in stars that lived and died long before our sun formed. We're made of stardust, as astronomer Carl Sagan beautifully expressed. Every atom of calcium in our bones, every atom of iron in our blood was created through nuclear fusion in stars or in supernova explosions. We've learned that space-time itself is dynamic, that it curves and bends and even expands. We've learned that time is relative, flowing at different rates in different places. We've learned that black holes exist, objects so dense and with gravity so strong that they warp space-time into regions from which nothing can escape. We've learned that gravitational waves ripple through space at light speed, carrying information about cosmic collisions billions of light years away. Gravity connects everything in the universe through the elegant geometry of curved space-time. It shapes the formation of planets and stars from collapsing clouds of gas and dust. It binds together galaxies containing hundreds of billions of stars. It drives the evolution of the cosmos itself, from the Big Bang through the current era of galaxies and stars, and eventually toward the far future heat death. Understanding gravity through general relativity represents one of humanity's greatest intellectual achievements. It required centuries of observation and careful thought, from Galileo dropping objects from towers, to Kepler mapping planetary orbits with unprecedented precision, to Newton unifying terrestrial and celestial mechanics under one mathematical framework, to Einstein reimagining the very nature of space and time as a unified, curved geometry. Countless others contributed through patient testing, precise measuring, and continuous refining of our theories. Yes, gravity limits us in certain ways. It makes interstellar travel incredibly difficult. It constrains how fast we can travel and how far we can realistically go given the energy requirements and time dilation effects. But gravity also enables everything we value. Without gravity, stars wouldn't form in the first place. There would be no nuclear fusion, no energy sources beyond the primordial heat of the Big Bang. Planets wouldn't exist because there would be no way for matter to clump together into structured objects. The universe would be nothing but a thin gas spreading through space forever, becoming ever more dilute, with no structure, no complexity, no possibility of life, or anything interesting at all. Gravity is the reason the universe is interesting. It's why we're here to contemplate these questions. Gravity allowed stars to form, creating the heavy elements in supernova explosions. Gravity allowed planets to form from the debris. Gravity maintains stable environments where life can evolve over billions of years. Everything we are, everything we know, exists because gravity shapes the universe into a place where complexity can arise. Many mysteries remain unsolved. Dark matter and dark energy together comprise 95% of the universe's content. Yet we don't know what either one actually is. We've observed their effects through gravitational lensing, galaxy rotation curves, cosmic expansion, but we don't know their fundamental nature. Are they particles? Fields? Properties of space-time? We're searching for answers. Experiments deep underground are looking for dark matter particles. Satellites are mapping the cosmic microwave background with ever greater precision to constrain dark energy's properties. Telescopes are observing distant supernovas and galaxy clusters to measure the expansion history. Particle accelerators are searching for hints of new physics beyond our current understanding. The search continues on multiple fronts simultaneously. Dark matter was first seriously proposed in the 1930s, when astronomer Fritz Zwicky observed that galaxies in the Coma cluster were moving far too fast to be held together by the visible matter alone. In the 1970s, astronomer Vera Rubin showed that stars in spiral galaxies orbit at speeds that require far more mass than we can see. These rotation curves remain flat far from galaxy centers, when they should decline if only visible matter existed. Something invisible is providing additional gravity. Dark energy's discovery was even more surprising. Before 1998, most cosmologists assumed the expansion was slowing down. The universe might be open, expanding forever, but decelerating. Or it might be closed, eventually collapsing. But discovering that expansion is accelerating changed everything. Some unknown component with negative pressure, what we call dark energy, is pushing space apart. We don't know what it is, but its effects are undeniable and profound. Quantum gravity, the theory that would describe space-time at the smallest scales where quantum effects matter, remains elusive. At the Planck scale, distances around 10 to the power of negative 35 meters, and energies far beyond anything we can produce, space-time itself likely becomes quantum mechanical. Smooth geometry breaks down. What replaces it? We don't know yet. String theory, loop quantum gravity, and other approaches are being explored, but none are proven. The very early universe, the first tiny fraction of a second after the Big Bang, is still largely mysterious. What happened in the first 10 to the power of negative 43 seconds, the Planck time? Did time itself have a beginning, or did it exist in some different form before? These questions remain open. The interiors of black holes, where space-time curvature becomes infinite in our current theory, lie beyond our current understanding. What happens inside? What is the nature of the singularity? We don't know, but general relativity provides the foundation for all of this ongoing work. Future discoveries will build upon it, extending our understanding into new realms we can't yet imagine. The core insight that gravity is space-time curvature, not a force pulling objects together, will endure as a fundamental truth about how the universe works at its deepest level. Until next time, keep looking up at the night sky. Keep questioning what you see. Keep seeking to understand the cosmos around you. The universe is vast and complex, almost impossibly so, with billions of galaxies, each containing billions of stars, stretching across billions of light years. But it's also comprehensible. We can figure it out piece by piece. We are figuring it out, slowly but surely, building our knowledge through observation and reason. And you're part of that journey just by trying to understand these ideas. Every person who learns about the universe contributes to humanity's collective understanding. Every question asked, every concept grasped, adds to our shared knowledge. You're participating in one of humanity's greatest endeavors, the quest to understand reality itself. Thank you for watching tonight. And remember this one strange truth. You're not being pulled down by gravity right now as you sit or stand on Earth's surface. You're following a geodesic through curved space-time, the straightest possible path through the geometry of reality. The ground beneath you is accelerating upward, pushing you away from your natural path. You're surfing the contours of the cosmos itself, riding the curved geometry of space-time created by Earth's mass. How remarkable is that? How beautiful that we can understand it. We live in an age of cosmic awareness. For most of human history, gravity was simply an accepted fact of existence. Objects fell. The sun rose and set. No one questioned why. But over centuries, through the patient work of countless observers and thinkers, we've pulled back the curtain. We've revealed that what seems like simple downward pull is actually the geometry of space-time itself. This knowledge doesn't diminish the beauty of a sunset or the grace of a falling leaf. If anything, it deepens our appreciation. When you watch a satellite drift across the night sky, you're witnessing an object following a geodesic through curved space-time. Every star you see is a massive sphere held together by its own space-time curvature. The universe operates on principles we can understand and use to make predictions that prove accurate to astonishing precision. And yet, for all we've learned, mysteries remain. We don't know what dark matter is. We don't know what dark energy is. We haven't unified quantum mechanics with general relativity. Perhaps that's as it should be. A universe fully understood might lose some of its wonder. The fact that mysteries remain means there's always more to discover. For now, we can appreciate what we do understand. Gravity isn't pulling you down. Space-time is curved, and you're following the straightest path through that curvature. The ground pushes up, and that push is what you feel as weight. When you drift off to sleep tonight, you'll still be following your path through the four-dimensional fabric of space-time. Sleep well tonight, knowing that you're surfing through space-time on a small planet in a vast cosmos governed by elegant laws. We're the universe trying to understand itself. We're patterns of atoms that have become aware, that can grasp the fundamental principles governing reality. How remarkable that we exist at all. How beautiful that we can understand even a small piece of how it all works. Rest well. The universe will still be here tomorrow, waiting to be explored further.